in this question, we're asked to find the volume of an object of revolution that is defined by f of x is x squared, g of x is 2x, and rotated around the line x equals 0, and this is just a y-axis. So the first step in dealing with any object of revolution question is to determine what method we'll be using to determine the volume. And the way we determine this is we look at what our functions are defined in terms of, what variable. In this case, f of x is defined in terms of x, g of x is defined in terms of x, and our axis of revolution, these functions are being rotated around the line x equals 0. And so all of these are defined in terms of x, and because they're all defined in terms of the same variable, we can use the shell method here. If, instead, we were given f of x and g of x, and then our axis of revolution were y equals some arbitrary value, then we could no longer use the shell method without modifying our functions. We would instead be forced to use the disk method. But in this case, they're all the same, and we can use the shell method. Now that we know that, our next step is to determine what our domain is. We were not given a domain like we are in some problems, and so we must determine the domain for ourselves. So we do this by setting our functions equal to one another. We have f of x is equal to g of x. And I plug those in, so x squared equals 2x. Be careful, do not divide by x, because you will lose a 0 here. Instead, subtract the 2x over, so you have x squared minus 2x equals 0. And then you can factor out an x to get x times x minus 2 equals 0. And from there, we can solve for x equals 0 and x equals 2. And this is our domain. This is the lower bound, and this is the upper bound. So now we can write our domain as x is a member between 0 and 2 inclusive. And from here, we need to know which of these functions is greater on this domain. And when we do that, you can do it one of two ways. The first way is looking at the graph of the function, which is cheating in my book. The second way is to choose a test point and solve algebraically, and that's what we're going to do. We're going to choose some test point c, some arbitrary c. I did it again. Some arbitrary c, these need to be parentheses. It cannot include either 0 or 2. C cannot be your endpoints, but some point between 0 and 2 for a test point. And so we're going to choose c equals 1 because it is by far the most logical choice. So we're going to evaluate both of our functions at c. So f of c, f of x is x squared, and c is 1, so 1 squared is 1. And g of x is 2x, and when we evaluate that at c, it's just 2. And so we get g of c is greater than f of c. And what this means is that on this interval, because we chose a test point that was in this interval, all values within this interval are going to fit this inequality. And so we can broaden this just a bit by saying g of x, is greater than f of x for all values between 0 and 2. So 0 is less than x is less than 2. Notice we do not include 0 or 2 in that, because if we were to say 0 is less than or equal to x is less than or equal to 2, then we would also have to say that g of x is greater than or equal to x on that interval, because it is equal to x on 0 and 2. And we don't want to say that. That doesn't help us at all. What we need to say is that g of x is greater than f of x, and so we drop the equality sign there, and we're left with what we need. Okay, now that we have this inequality set up over the domain we're interested in, now we can use the shell method formula, which is volume, v, equals 2 pi times the definite integral on our integral over interval, of our larger function, in this case g of x, minus our lesser function, in this case f of x, times x. And this x is multiplied there because, and only because, our axis of revolution is x equals 0. If this were any other value, if it was x equals any other constant value, we would not multiply by x. Instead, we multiply by that other value minus x, that binomial. But because it is 0, we cannot do that because we would have 0 minus x, and that would make this negative when it does not need to be negative. And so in the one case when it's 0, it's special, and we just make it x. So from here, we plug in g of x, which is 2x, and f of x, which is x squared, into our function. That's all that happened. Next, I'm going to do two things. I'm going to, one, pull out a negative, because I like to order my equations with my highest degree in front, and my highest degree here is going to be x squared, and so I want to pull out that negative to make that a positive x squared minus 2x. And then I'm also simultaneously distributing the x. So it's going to be positive x squared times x is positive x cubed minus 2x times x is x squared. So I have positive x cubed minus 2x squared and a negative out front. From here, integrating is very easy. All we have to do is, again, negative 2 pi times x cubed. Integral of x cubed is x to the fourth over 4. Integral of x squared is x cubed over 3 times 2, so it's negative 2x cubed over 3. And again, we evaluate that at 0 and 2. And I would like to go ahead and pull out these numbers out of the denominators of these fractions, so I have nice, beautiful things to plug numbers into. But you could plug numbers directly into this and get an answer, but I prefer to take the scenic route and get everything nice and ordered first. And so I'm going to pull out, the lowest common denominator here is 12, so I'm going to pull out a 12 in the denominator, so I have negative 2 pi over 12, which simplifies to negative pi over 6. I just didn't write it. And to do this, I need to multiply this by 3, so I have 3x to the fourth, and this by 4. So I have negative 8, 2 times 4 is 8, x cubed evaluated from 0 to 2. Sorry for the interruption, I just needed to turn my paper over. Okay, so what I did next is I pulled out an x cubed inside the integral here. And this was before 3x to the fourth minus 8x cubed, and I just pulled out the x cubed, and we're again evaluating at 0 and 2. And from here, it's as simple as we can make it, so let's go ahead and put in our numbers. So we have x cubed, I'm going to evaluate that at 2. 2 cubed is 8. 3 times 2 is 6, minus 8. And then when we evaluate it at 0, well, 0 cubed is 0, so it doesn't matter what's in here. So this is just 0. And this 0 is going to disappear, not really important. But what we have now is we have negative pi over 6, I miswrote a second ago, times 8 times 6 minus 8. What jumps out at me is there's a 6 in the denominator and an 8 in the numerator, and we can simplify out at 2. So I will do that. I will factor out a 2 here and here to make it 3 and 4. So I have negative pi over 3 times 4, and I also subtract it here. 6 minus 8 is negative 2. So we're left with negative pi over 3 times 4 times negative 2. And here I'm taking it one baby step at a time just to make sure that I can follow. V equals negative pi times negative 8, 4 times negative 2, over 3. So the only thing left is to cancel our negatives and we're done. We have 8 pi over 3, and that is the volume of the object of revolution of this.